Okay, and one more thing is about on how to characterize in terms of material properties. Because if you want to make the device, not only you have the optimized design, especially on the structure, but also you need to have the optimized materials. So you need to have a suitable material to obtain the maximum power output. And then last week, I had introduced to you about energy conversion, mostly on the indirect energy conversion. So when we say about indirect energy conversion, it relates at least 2 or 3 kinds of energy transformation. For example, we have looked on the thermal power plant, where we convert the thermal energy, and first we boil the water to become steam, and then the steam will go to the turbine, and that turbine will rotate. That is the kinetic energy. And then from that kinetic energy through the shaft, it will go to the electromagnetic fields, which is the generator, and then it will produce the electrical energy. So we have 3 kinds of energy transformation. So that kind of energy conversion, we call it as the indirect energy conversion. But in this class, I think starting from today, we will look on the solar cell, the photovoltaic, which is one of the direct conversion techniques. I think most of you are familiar with photovoltaic and solar cell, and I think you all have them in your undergraduate studies, especially for you all who are background from electrical engineering. Undergraduate studies, if you are focusing on electrical engineering, maybe you have focused on the PN junction type of solar cell, where we fabricate the solar cell based on the N-type and P-type semiconductor. So we will look in detail how to the structure, a little bit on physics, because you all already understand what is the phenomena or what is the physics behind the PN junction solar cell. And we will look at today, targeting to finish until photovoltaic today. Okay, so let me revise a little bit what we have. Sorry, I teach master only one semester, so I did not use this for one semester. Okay. So last week, we had looked on the basic. I think this one you already learned in high school, or if you are Malaysian, in matriculation or in undergraduate studies, about the fundamental of energy. The main point is the energy is conserved. That is the basic fundamental, especially when we say about the law of thermodynamics. We have two law of the thermodynamics that we will use in this course. The first one, energy is conserved, and the second one, the entropy will keep increasing, which means that ultimately it will become randomized the energy. Then so after we have looked on the fundamental, we have looked on the indirect energy conversion. We have looked around 4 or 3 kinds of the big one that can produce much power output. We have looked on the hydro, we have looked on the thermal, we have looked on the fuel cell, and we also have looked on the wind. Mostly between 4 of these is indirect. The fuel cell is indirect. In this course, we not discuss in detail about fuel cell because we will focus on the solid state energy conversion devices. So I think we will not discuss about the liquid energy devices. When we said about the hydropower, as you all know, we convert from the potential energy to the kinetic energy and we use generator. So generator will transform that kinetic energy into electrical energy. And then we have looked on wind. Wind also same. The wind flow that rotate the turbine, and then we have the generator again, it will convert into electrical energy. For this case, if you remember, we have that the so-called Betz limit, that we cannot convert all the flow or the kinetic energy of air into electrical energy 100%. We have limitation which is around 58 to 59%. If you possibly can convert 100%, it means that all particles of the air will be stopped at the turbine, which is will not be able. So you have the limitation around 58 to 59%. And then we have looked on the thermal power plant. So about conversion of the thermal energy into electrical energy, I think this is the conventional one. So you burn something, you burn the coal, you burn the oil, you burn anything to heat up the water to become the steam. Okay? So when we deal with this kind of heat, usually we will have the thermodynamic cycle. So I have explained to you about two kinds of thermodynamic cycle. One is called the Carnot cycle, which is the ideal heat engine that we can convert into a closed cycle. We can convert that heat input or the thermal energy that we apply to the system, and then it can convert some useful work in terms of ratio between high temperature and the lower temperature. So that is the limit. So the one which is the 100% will be minus with that ratio of the Carnot cycle. And when we discuss about thermoelectric later, we will look at the efficiency of the thermoelectric power generator also will be limited by that Carnot efficiency. But it has some plus, some surplus, which is the influence of that thermoelectric power generator efficiency itself. It cannot be more than the Carnot cycle. Because if you see the TS diagram, the temperature and the entropy diagram, Carnot cycle have a square shape, which is the more surface area that we can obtain inside the cycle. But the other kind of cycle, like the Rankine cycle, it don't have the square shape. Much more smaller, the surface area. So it means that the useful work that we can produce from the heat that we apply is more smaller if you compare with the Carnot cycle. So we have looked on the Carnot cycle. This one, as I mentioned, the efficiency is the limitation between the low temperature and high temperature. If you want to increase the efficiency, of course, you need to increase how much the energy that you need to apply, which is in terms of the heat, the higher temperature. But the challenge is how can you keep the lower temperature side. Same goes in the thermal power plant. You need to cool down the water, and then the water becomes the water, not the steam, right? But it don't go until below that 0 degrees, right? So if you can keep a big temperature difference, a high energy input, so you can have a higher efficiency. And then we also had discussed about the Rankine cycle that has been usually used for the generation of electricity by using the thermal power plant. And then lastly, last week, we also had seen about the fuel cell. I think if you look on the Yahoo News, the current news, and so on, people are arguing, especially in the electrical vehicle car. Either we want to go through battery, or we want to go the engine to the fuel cell. But currently, there are some rumors that fuel cell not anymore in the picture. Not sure. So the fuel cell is clean energy, and it's quite simple to produce the electricity from the fuel cell. because the structure is you need two kinds of electrode, and then you need to have the electrolyte. So what happens is we have the chemical reaction, which is the oxidation and reduction happen between the electrolyte, the fuel, and also the electrode. So that giving and receiving the oxygen and giving and receiving the electron will allow the electron, when you have the current, the electron flow, it means that you have the current that flowing through the loop. So that kind of electron can be produced by using that, we call it redox couple or reduction and oxidation process. So that is how the fuel cell works. But if you compare with the conventional one, the fuel cell needs to be stacked because depend on the material and so on, the ideal voltage around few volt. So you need to make a stack or stacking the fuel cell in many fuel cells inside one system so that you can have a bigger output voltage. Okay, today we will start from the terms of energy harvesting. When we say about energy harvesting, or if you want to say about the production of electricity, people will ask you, is this a power generator or is this a power harvester or energy harvester? So how to differentiate those things? Usually the generator will produce a very large power output, not in terms of milliwatt, usually more than 1 kilowatt, 10 kilowatt, something like that. But if you say it is the energy harvester, as it would, it harvests the energy. And usually we will imagine we harvest the energy from our ambient. So when we say about energy harvester, it will be related with a small production of power output, around milliwatt, and sometimes can be microwatt, sometimes can be nanowatt. So when can we apply this kind of small power output device? Usually this kind of device are used for the portable system and also the stand-alone system. Or we call it the self-powered system. Because usually when we want to use the small electronic devices like the node, the sensor node, and so on, it will need around milliwatt, no more than a few watt, a few, maybe few watt, or few milliwatt, few 10 milliwatt, something like that. And this kind of energy harvester can help to produce that much of energy. One of the challenges why it's still difficult to apply is the efficiency, correct? Still low. Other than that, yes, cost. It's not feasible. It is possible to make a self-powered system, but for you to sell it in the market, it's not feasible in terms of cost if you compare with efficiency. If the efficiency is very big, 80%, 90%, can be acceptable even though the cost is high, but the efficiency is still low. I think one of remarkable advancement inside the renewable energy is the photovoltaic. You can see the photovoltaic, the solar cell, rapidly improve from around few percent. Right now, today, we can have around 40% of efficiency. And you also can see the cost remarkably reduced. And before this solar cell can be equipped inside the small devices, like the watch, like the calculator, and so on. But right now, you can see it can be farmed, solar farm. It can compete with the other conventional type of power generation, and it also can contribute to the power distribution system. However, the problem is, one of the problem is we cannot harvest throughout the whole day because it needs solar irradiation. You need to have the day and night. In the night, depending on what kind of material that you use, you cannot harvest, you cannot get the solar irradiation. So how can you generate electricity from the solar cell? So if you want to make a solar farm and so on, you need to have a storage medium. For example, like the battery and so on, store the energy. Okay, when we say about energy harvesting, I think one of the interesting, what we call it, implementation. I think you have heard about IR 4.0, right? Industrial Revolutionary 4.0, which is the interaction between humans. When we say about that, it's more on the manufacturing side or more on the industrial side. But some countries use the other kind of model that we call it Society 5.0. How many of you have heard about this? So they use this term, Society 5.0, to include the society inside that mix. If IR 4.0, mainly for manufacturing. This video, I think I don't plan to play because it's from YouTube. If you have time, you can Google on YouTube Society 5.0 and you can watch it. If we have time today, I will go back and play it for you. But the main point is for the Society 5.0, I think last month or last week, that Elon Musk has informed, has announced the Optimus, the robot, right? You look at the news. That he planned to sell the robot. Look like the movie Terminator. And the price is around $20,000. The target. So to make this kind of thing happen, we need the power source. Portable, long life, and so on. One of it is battery, and the other than that is energy harvesting. So in our daily life, in Society 5.0, we want to have the drone, we want to have the sensor following us. All of that need the power resources that can be portable, lightweight, and small. You cannot have a big one. You can apply the indirect conversion technique, but if you want to put the generator on the drone, it's very big. Might be you cannot fly the drone at all. Might. Okay, so in the Society 5.0, all the things might be become portable, easy to reach, and one of the challenge is the power source. Okay, so let's look in terms of So just I mentioned, when we speak about the concept of energy harvesting. So it means that it will use the ambient energy to produce the electricity. So when we say about the ambient energy, you can see over there, we can have vibration. We can have electromagnetic energy, which is the solar radiation. And then we can have heat, thermal. All of you have signed. And then please also read the survey inside the spectrum. I put some question over there to check your understanding about the last class. Where am I? The energy resources. We can have vibration, we can have solar, we can have thermal. I think back 10 years before, I forget the brand name of the watch. If you remember, there are watch in the market that can be powered up by only wearing. So the power is come from the chip from the board. So it can produce the electricity for the watch. So that is one example on how can we make use the ambient energy. But let's go back in the fundamental when I discussed with you all last week. You need to know where is the energy come from and how to convert it before you can make this energy harvesting. Even though you know that the thermal energy, the waste heat is over there. For example, like your computer right now, sometimes you feel the heat. But if you do not know what is the conversion technique that can be used to generate electricity, no meaning. So that's why you need to have some kind of knowledge how or what is the energy technologies available to convert that ambient energy into electrical power. Okay, so if you look in this table, the vibration, the condition, 1 meter per second or 2. It can produce around 100 microwatt power density per centimeter power cube. And then, if you consider in terms of joule, it's around 8.64 joule. How much this energy? You can look back at the table that I have explained last week. If 10 joule, like swinging a pen. Solar, you can see all that. Depending on how can you absorb the solar irradiation, outdoor and indoor difference. And then thermal, temperature difference 5 degree, microwatt, 2.59 joule. Still small. Okay, so when you have this kind of device, the conversion device, sometimes we call it as energy harvester, we can call it the transducer, and so on. It can go to the energy management, or it can go to the storage. Energy management is mean that, for example, you put rectifier over there. You need to convert, for example, from DC to AC, or from AC to DC. Or you need to increase the voltage, but reduce the current, for example. And then, if you have collect or you have harvest the energy, you need also to store the energy to use for the whole. So you also need battery. Then you can power up all the electronics component like the sensor and microcontroller. You can go direct or you can go in the storage to be used in your electronic device. Okay, we can see that around microwatts right now. Okay. So if you see the example, I think this data is a little bit old, but right now we have much improvement on the power consumption of electronic devices, much lower than this. For example, like the sensor nodes, it needs around milliwatt, just I mentioned. So before this, we can see like the vibration can produce around few hundred microwatt, enough to power up the sensor. Like the thermal, we can produce around few 10 microwatt, enough to power on the sensor. Okay. If you compare with the mobile desktop server, it becomes very large. So you cannot have one energy harvester. Like the fuel cell, you need to have a big system that you stack it together to have a bigger power. Okay. If you see here, the revolutionary or the improvement in the power consumption of electronic devices, this is the power consumption by year. So all data, 2008, right now 2024, 16 years back. You all have you all heard about this? MP3. Who has expressed music? The sound of the earth. For those who do not know, MP3 is a small device that you can bring anywhere, portable, and then you can play music without bring cassette or MD or CD. You know CD? So that MP3, for example, I just put the old kind of information because I want to recall that our system for MP3. And now you just bring your handphone to hear music. Back on that years, you can see from 2002 to 2008, they or the engineers, the researcher can reduce the power consumption from few hundred milliwatt, less than 100 milliwatt, few tens milliwatt. So it tells us that energy harvesting has quite a lot of potential to be applied. Okay, the form of energy. I think when we discuss about energy, I think there is no clear cut or standardized. What is the type of energy? I think you all know, generally we can say we can have two types of energy. One is this, what? The type of energy. Or potential energy. The other one, kinetic. Potential and kinetic energy. But when you learn in high school, matriculation, undergraduate, you heard about chemical energy. You heard about mechanical energy. You heard about electrical energy. Is electrical energy is potential energy? Or is kinetic energy? It's quite a question mark, right? Even though we have learned many times before, right? That's why, as I said to you, it's quite difficult to find some standardized things. But usually when we discuss about energy, generally it can have two types, the potential and kinetic. And it can have several forms. Usually we can consider 6 forms of energy. 6 forms: mechanical, chemical, electrical, electromagnetic, nuclear, what? Thermal energy. And then that 6 forms of energy can be kinetic, can be potential. How come, right? I'll give you an example. In electrical energy, usually when we want to characterize the electrical energy, we consider the power. Before that, what is potential energy? Potential energy related to what? Position.
Potential difference.
Yes, potential difference. Or the position. Like the water reservoir, you need to have some height. Because it's come up with the equation mg h. H is the height. So any kind of object that has some height, it has the potential energy. Easy to understand. How about kinetic? Movement, very good. Kinetic will be related to the movement. Okay, let's jump back to electrical energy. I just mentioned, if we want to characterize the electrical energy, we will consider the power. The power is equal to current multiply with voltage. Power is characterized or equal in general I multiply with V. Okay. When we say about this power, what is the object or what is the thing that define that power? Electron, right? Electron. So electron can have both potential and kinetic. Just you all have agreed with me before, kinetic is the movement. So when electron flowing is mean there is a current. So that is the kinetic energy of that electron because it flows inside the material or inside a medium. Okay, voltage. Voltage is defined what? What is the unit of voltage? Volt, correct? From what? Volt is equal to what unit? Joule per coulomb, right? If you go back, the definition of the voltage is the force to push the electron. Yes, to push one charge. So it means that to put the electron at certain level. That's why the voltage we call it as the potential energy. The electron has the potential energy. So that kind of sixth form, as I mentioned just now, electrical, thermal, and so on, might be can have either potential or kinetic. Like the electrical can be both kinetic or potential. If the chemical energy, usually hard to find kinetic energy. Mostly is related to potential because the chemical energy is the stored and medium. For example, like the gasoline. I give you an example before. The gasoline that we put inside the car, so the energy is stored inside a liquid, which is the gasoline. Okay, that's its form. We can have mechanical, we can have thermal, we can have electromagnetic, we can have chemical, and 1, 2, 3, 4. Magnetic, electromagnetic, we can go to one. 4. For example, in this case. So this is from our ambient that we can harvest. What kind of tools, what kind of device what kind of transducer that we can use to harvest that energy. For example, like we had discussed before, the kinetic. We can make use the generator to produce electrical energy. I think in undergraduate studies, if you are from electrical engineering background, you have learned about machine and drive. And then you also have learned about electromagnetic, the Lenz law and so on. When you have the flux that cut the other field, you can produce electrical field. That is what happened inside AC and DC generator. Okay, if thermal, what you can use? You can use pyroelectric. You can use thermoelectric to generate electrical energy. Vibration from the mechanical, you can use piezo. Electromagnetic from radiance, you can use photovoltaic. And all of this, just I mentioned before, it can go to the energy conditioning to convert it into AC, DC suitable for your devices, and then can go direct to your device or can go first to the storage. So for this course, just I mentioned before, we will look this piezoelectric, one form, the mechanical energy. And then we will look this pyroelectric and thermoelectrics, one form from the thermal energy. And we also will look this, the photovoltaic, one form from electromagnetic. So this is what we discuss throughout this 14 weeks to discuss. Okay, let's read that a little bit in brief about this kind of energy conversion. The first one about the mechanical energy, we can use piezo, we can use electromagnetic, or we can use electrostatic technique, all related to the movement of the device to generate electricity. And in this table, you can see here, depending on the frequency also, we can have this kind of vibration, 40 Hertz, 30 Hertz, 23 Hertz, 16 Hertz, especially this one at the vehicle. They are wasted energy. If you can make use it, a lot of energy can be produced. But until today, we cannot see is implemented what. Maybe some of research put on the road some piezo, and then the car move can generate electricity. And sometimes if you go to the science museum, they put on the stand. When you walk on that, it generates a lamp, the light for the stand. Piezoelectric, electromagnetic, electrostatic generator. This one, I think we can just skip. We will discuss detail later about that piezoelectric. Usually piezoelectrics, when you apply some force to the material has the ability to have a distribution of the charges. So when you give some force, they are more positive, they are more negative at either side. So when you have the distribution of the charges, you will produce what? Voltage. More positive, more negative. You have the voltage. But if you keep press, the charges is not changes, it's not change. There is no flow, only potential. That's why you need vibration. You need to change the potential in order to let it interact with the other electron, so that you can have the electron to flow inside your circuit. so that you can have the current and also the power. Same goes over here, like the electromagnetic is the flux. I think you had this kind of experiment in your undergraduate studies. You have some coil, and then you have magnet, right? And then you connect your coil with ammeter, and then you just move your magnet, and then you can see there is reading in your ammeter that show the changes of the flux will produce current or produce voltage. So this is also the example. The first one about the piezoelectric. This one about the capacitor. We change the charge distribution. This one, when we discuss later, piezoelectric can have either the same direction with the force to produce the voltage, or in normal to that force that we apply that will produce the voltage. This is typical example, PMG70 micro generator. So you can see here, depending on the weight, depending on the frequency, it can produce around 1 to around almost 100 milliwatt power output. Radiant, the electromagnetic, the solar irradiance. So it depends, for example, in this table, you can see you have the fluorescent tube, you have halogen lamp, you have from IR wave. So based on this irradiation, you also can produce power. So JSC is the current density for short circuit. VOC is open circuit voltage. FF, field factor. I think when we discuss about the photovoltaic, we will look on what is this field factor. And then the efficiency and the maximum power that can be produced in terms of power density. And usually when we discuss about energy harvester, we will discuss about power density per volume or per size. So if you are using photovoltaic, you need to have a big size. So in terms of power density, then it's not very good. If you use thermal, it's not really important the size, but how to keep the temperature. Maybe you can meet in terms of power density. Okay, RF, radio frequency. That kind of wave, we also can generate power. So you can see here in this table, radio station, base station, mobile phone, Wi-Fi router, okay, and then distance 5 or 10, 100, 500, 1 kilometer, 1, 5, 10 meter, 1, 5, 10 meter. Respective to this distance, this is the possibility, the power that you can produce. I think maybe some of you know about the phenomena near to the what we call the power distribution tower. So if you bring the lamp, fluorescent lamp, for example, and then you just put it on the ground, it can switch on. Wi-Fi router, you can see over there. So right now, we are living in the world that we cannot live without internet. How many days that you can stand without internet? I think we not more than 10 minutes. I think for Muslims, after you pray, you just put out the handphone. Okay, your handphone. When you buy a handphone, did you read the electromagnetic quotient, the radiation? We have standard that the phone cannot exceed some sort of radiation. I think the old people usually don't use messaging because all time messaging you need to pay. One message 10 cents, 20 cents. But right now it's free, and they prefer to call. When you are calling someone, you can see or you can touch your hair become hot. Right? So there is some radiation that produces the heat near to your brain. And if you open your handphone and the specification, we have the standard. I forget the name. There is standard, the value the phone cannot exceed more than certain value in order to protect your brain and so on. And there are also some works that discuss about will this kind of electromagnetic radiation harm our health, especially in terms of cancer. So maybe after this, when you want to choose the phone, not only choosing the brand, but maybe you can check the electromagnetic radiation. So that kind of electromagnetic things, you can imagine if we can make use or we can produce a device that can convert that wave into electricity, we become rich. Because there are too many right now. So how can we convert it into electricity? This is some way that we are using the rectangle. So we have the antenna, and then we have the impedance matching, and then we have the rectifier, and then you can produce electricity. There are several works has been done in order to produce electricity from this kind of system. But usually,
wouldn't the practice actually weaken the signal and prevent the transmission?
Yes, this depends on what is your purpose. So usually this kind of thing is designation as the signal. But if you take it to produce power, this might influence the signal. Because the signal also electrical signal, the current and also the voltage. But usually the signal will be changed into 1010, on off. And sometimes the device needs until 5 volts. So if you take the energy less than 5 volts, it will influence your information system. Just one way how to harvest the wasted signal. This one, this one you can do that. Okay, one more thing, the heat. If you see here, this is base 2005, and this number is petajoule. Petajoule, 10 power of 15. And this line shows the waste heat that we produce. And you can see here, we divide into low, medium, and high. In this case, they categorize the low as less than 100. The medium is until 300 degrees, around that, and high, more than 300. And you can see how big this orange line that become a low waste heat. And usually it is said that around 30% to 40% of the waste actually is very much the waste heat. And if you can build, you can fabricate, you can design energy harvester that can make use of this low heat, it's quite a lot of potential of electrical energy that you can obtain. Okay, so depending on the temperature, why the low heat is quite difficult to be harvested, because when the heat is too low, actually the application is limited. But for the medium and high, it's quite easy. For example, in the thermal power plant, when you have quite high temperature, you can give the heat to heat up the water in the residential house to become the hot water. But if the heat is low, you cannot use it. You need to find the other means to use that waste heat into electrical or some useful work. Okay. Okay. For the thermal, we can use thermoelectric, we can use pyroelectric, we can use thermomagnetic. We will look in detail that too, thermoelectric and pyroelectric. Thermoelectric, usually it will depend on temperature difference. If you have any temperature difference, you can produce electrical power. But the challenge is how can you maintain that temperature difference. Pyroelectric, people not only use that pyroelectric to produce electrical power, but also for imaging system. Pyroelectric use the fluctuation of temperature to produce electricity. There's a difference. So when you have a fluctuated temperature at a certain frequency, you can use pyroelectric technologies to produce signal or to produce electrical power. So this is just typical example. We will look in detail after, I think, around week 3. So the thermoelectric power generated based on some effect. And the most popular effect is the Seebeck effect and Pao-Chair effect. The Seebeck effect related how much the temperature difference that you apply, you can obtain the voltage. And then for the pyroelectric, this is typical example of thermoelectric power generator. Usually we call it as the PEG. Quite small, this kind of module. But you can stack it and become look like this or look like that. The thermoelectric has been used in NASA for their aerospace shuttle to produce electrical power. And then the pyroelectric, also simple, look like QC. You need electrode, you need pyroelectric material, usually a ferroelectric material, and then you need the temperature fluctuation, this dT over dP. And then you can produce power. Very simple. But where can you find the fluctuated temperature? At specific frequency. Quite difficult to find. Where is the temperature is fluctuated? If you see in this book, is there any resources of the fluctuated temperature? Okay. So next, we will start about the photovoltaic. I think that's around 15 minutes. So we start back at 4:15. How many of you are from UM? Undergraduate? From University Malaya, undergraduate. How many international students? So you're from China?
Yeah.
From Bangladesh, Indonesia. Is this your first time in Malaysia?
Yeah.
How do you feel Malaysia? Okay. How the food? Okay. Nice. Yes. Yeah. Have you tried Mama Stall? Mama Stall. Kedai Mama. Mama Shop. You should try. Have you tried roti canai? Chana and not yet. If you go to Mama Stall, it's a restaurant, and easily you can find anywhere, especially in Kuala Lumpur. So they sell the food of Malaysian Indian food. Yes. Normally for Malaysia, if you want to spend a lot of time, you will go to the Mama Stall, and you can order anything, almost anything. And one of the famous food is breakfast, roti canai. Roti canai and teh tarik. But it's not good for health. Too sweet. If in lunch hour, nasi kandar. I think you know the Q Bistro, the food restaurant at Jalan Bangsa, the front gate. Have you seen the shop, the restaurant? So if you go there, you can try nasi kandar rice. So it used Indian spicy, like the curry and so on, and then with chicken. Combinations. Nasi kandar. Hey, right now you all live outside from here, in college. Outside, yes. How many of you from electrical engineering? Other than electrical engineering, mechanical? Telecom? Telecommunication? Physics? Other than that, it's electrical. All of you electrical. Okay, so let me start back our class. So we will start on photovoltaic. Before we discuss about the device, the physics behind it, the material and so on, let's look a little bit on the standard test condition. Usually when we want to test the solar cell, we will use one of the parameter. We use this one, a mass coefficient, which is the direction of the solar irradiance. Either is in plane, like the solar are in plane, the radiation are in plane with the Earth's surface, or have some degrees. When we have AM 0, it's mean outside from the Earth. When AM is 1, which is cos 0, right? Cos 0 is 1, so it's mean right in normal to the surface. And usually, when we want to test our solar cell or PV module, we will use 1.5, AM 1.5, which is 50% longer than the shortest path that we have of solar irradiation. Okay. This AM 1.5. So when we say about solar cell, I just mentioned before, this electromagnetic or the light, usually we will call this kind of energy as a photon energy. And this energy of the wave or the irradiance, I think if you recall back, you have learned E equal to H mu or F, frequency. And the frequency is related with speed and also wavelength. So that photon energy is described or is defined by the wavelength. For example, this graph shows us the sunlight intensity as a function of wavelength. And there are two lines over there. One is AM 0, the red one, and one is 1.5. And you can see here, the sunlight intensity have a peak at a certain wavelength. So if you have this kind of data, and I ask you to design and optimize solar cell, I give you, or I ask you to choose what kind of material that you can propose to me based on that blue line. What kind of material that you can propose to me is good to be used to make use this solar intensity at AM 1.5. Anyone can suggest me material? If you do not remember what kind of material, maybe you can say about material properties. This kind of material properties is good to be applied for this sunlight intensity characteristic. Anyone? Usually solar cell is made from what kind of material? Silicon. Very good. Silicon is a conductor, semiconductor. Is a semiconductor. Why we use semiconductor? We use semiconductor because we can alter the electrical properties of that material. And based on this data, if I ask you, what is the best material that you can propose to me? And then you know that the energy is depend on the wavelength. So you need to choose a material that can absorb, especially at this peak, that much of energy. So what kind of material that you can propose? Semiconductor, very good. And it depends on the band gap. So you need to find the band gap that have the specific energy that can absorb this much of energy. For example, if you have 0.5 wavelength over here, and it can be translated, for example, around 1.5 electron volt. If you use a semiconductor material, your friend said silicon. Silicon has a band gap around 1.12 electron volt. So you can see that sunlight are enough to excite the electron to allow a free carriers. That free carriers, as I mentioned before, that electron has that kinetic or potential energy. So roughly based on this, if you put any measurement around the world and you check how much the energy, depending on the wavelength, roughly you can propose what kind of material the best to absorb that photon energy. First, you need to absorb. If you cannot absorb, no need. Right. For example, if you use the band gap larger than 1.5, for example, 2 electron volt, and you put at the place have the energy of solar irradiance 1.5 electron volt only. What happens to that energy? It will not absorb. You will see a transparent material, right? Because the energy will just go. The energy is not enough to break the bond, the bonding between electron and the atom, to make it free to move inside the material. So this is roughly you can propose if you know this kind of energy. So right now you know what is the energy resources, yes, solar irradiance, and you know how much the energy depending on the wavelength, and roughly you can find what kind of material. Okay, I think if you are working or you do some project with the solar cell, maybe you have used some of this kind of technology, the tracker that track the sun. And this graph shows us the radiation average daily throughout a year. And there are 3 lines, the green, blue, and red. So that kind of irradiation, we consider the AM and so on, is also depend on the latitude. So each phase has its optimized condition. So if you do not do any kind of optimization, like normal to the ground, so this much, only this much of energy that you can use. If you find the suitable latitude, you can have this much of increase at a specific mark. If you use the tracker that track the sun, this much you can have. At the previous slide, we see that we optimize at the material level, and at this side we optimize the position and also the design of the system. So it's not only you can optimize enough to optimize the device, but you also need to consider how well can you get that energy resources. Okay, just some for your information. I think you all know photovoltaic can be applied as integrated with the building. Okay, you can see, I think Malaysian is not widely used yet, but you can see some house that have on the rooftop have the solar panel. And then in Malaysia, currently we already have solar farm, quite numbers. And then we also have floating solar farm on the water surface. Because just I mentioned before, the solar panel or the solar cell need to have a big surface to absorb more radiation of electromagnetic. But it will increase the cost of the place. You need to have quite a huge place. Then you need to pay to get up there. This one, I think you can just read. So this thing, you usually see at the solar panel. You can see over there, we can have gaps, the red color over here. And then you can have the bars, and then you can have fingers. So this one, we call it as the PV panel. The gaps, this is the function. The fingers is the conductor, and that is the function. That's why we are using conductor to collect the power. This one, also we use conductor, metal, all to connect all the solar cell together within that is PV panel. And then you can see the terms, solar cell, module or panel, and array. So you can see over there what is the thing. Today we will discuss this one, the cell, the height of the system that convert the photon energy into electrical energy. Before this, I just mentioned to you all the standard test condition. Usually this will be tested at a solar cell or a PV panel, already completed the device. And we will consider this parameter, irradiance 1000 watt per meter square at temperature 25 and solar spectrum at RMS 1.1. So we will test at this condition and we will measure the power output, for example. And then this is just roughly how to calculate per year. This one also you can read. Okay, this one, I think you have learned in undergraduate studies, right? How many of you still remember? Okay. So the solar cell can have this kind of equivalent circuit. So this part is the source that generates the current IL when we expose it to, or when we give the photon energy. And then we have a diode and two resistors to model solar cell. That diode will not allow the current to flow at opposite direction. And these two resistors, one we call it the series resistor, and one we call it the shunt resistor. The series resistor is modeled due to the resistor due to the contact in the solar cell or outside with the circuit. And the shunt resistor usually we consider as the leakage current due to the defect and also the recombination inside the solar cell. And you can see here, this current that flow to your load, for example, or the potential that has been applied to the load, the output is governed by the balance between this diode and the shunt resistor. What it means that if you increase the shunt resistor, the current that flow to your load will decrease because it's go to the diode, but the voltage is keep high. If your shunt resistance is lower than the diode, then the current can go to the load. So that is the what we call it in English, the trade-off between the current and voltage. So if you plot the IV characteristic of the solar cell, the y-axis is the current, the x-axis is the voltage. So this one is depend on the diode characteristic. One, the current, total current produced by the photocurrent minus with the diode part and also the shunt resistor. And you can see here, you cannot have a maximum voltage at a maximum current. If you increase the voltage, the current will be reduced. That is the trade-off between the diode and the shunt resistor. And the maximum power, the highest voltage, the highest current at this point. So that is the maximum power that we can get from that solar cell. So this is how we model in terms of circuit for that solar cell. If you open the circuit, you will have the maximum voltage, but the current may not flow. That one we call it as the VOC. If you close the circuit, the voltage will be 0, but you will have the maximum current. But the maximum power on this point, okay, that you can obtain. So this is the characteristic of the solar cell. So if you want to characterize the solar cell, you need to measure the IV. Under what condition? That standard test condition. Okay. In last slide, I have shown you a table that states about field factor. So what is the field factor? FF. So FF is the ratio between the maximum power equal to maximum voltage multiplied with that maximum current divided by open circuit voltage, short circuit current. What is mean that what is the ability of your solar cell to produce the maximum power compared with its open circuit and short circuit current. You know that open circuit voltage is the maximum voltage, short circuit current is the maximum current. So if you can get one, which is not possible, get the one. This FF, field factor, will also influence by the temperature. Same goes to the VOC and ISC. That's why if you do some literature review related to the solar cell development, one of the problem is the temperature. When your solar cell become hot, the performance will drop. That's why we also use two kinds of cooling system, either active cooling or either passive cooling. Like the floating solar cell, we are using the passive cooling system. We make use of the water to cool down the temperature of that solar panel. Some basic calculation. Consider a crystalline silicon photovoltaic cell has an open circuit voltage 0.6, short circuit current 2 ampere. And if you do at the standard test condition, the fill factor is 0.75. From this value, we already can estimate how much the maximum power that we can obtain from this solar cell, from the equation. Again, the FF is the ratio between the maximum power divided by the VOC and ISC. So roughly from this equation, you already know what is the FF value. You already know about the short circuit and open circuit current and voltage. You can calculate how much the maximum power that you can obtain from this kind of solar cell. However, if you put your solar cell at a certain place, in this case, a temperature of 55 dB. You know that the previous example at the standard test condition, which is 25 degree, but right now you put at 55 dB. So how can you calculate it? You can use that equation, which is valid for silicon, that FF is also as a function of that delta T. VOC is also as a function of that delta T, and ISC is also a function of that delta T. You just use that equation. Roughly, you can compare how much percentage that the power output has reduced. Try to calculate it, and if you calculate it, you will find the increment of 30 dB. You will reduce 11% of the output of the solar cell. So this equation is not valid throughout the solar cell. It depends on the type, depends on the material. For this case, that crystalline silicon. Okay, the type of solar cell. Roughly, we can have 4 kinds. Wafer-based, multi-junction, thin film, and imaging technology. I think right now, if you read Yahoo News, scientific news, so on, the hot news is known, perovskite cells. And the production can use printing technique. There is, you can print your solar cell, and then you can use it. And right now, the efficiency is quite also high for this perovskite. Most of the researchers right now are going towards this perovskite solar cell. So we can divide into this kind of 4 wafer-based, multi-junction, thin film, and imaging technology. In this class, we will look on PN junction and the SST, dye-sensitized solar cell. Okay, if you are familiar with the solar cell, the solar cell research, I think you well know this kind of diagram. I didn't put the this from this National Research Center and right, United States. So this is the not roadmap, but the progress of the solar cell, depending on the type: multi-junction, crystalline, thin film, and imaging. So you can see here 2025, 2000. In 2023, this data. You can see here almost 50% the efficiency of the solar cell. Nice try. If you compare with the thermal power plant, only 40%. And then the color, you can see the type. And you can see quite a sharp improvement in that imaging technology. As I mentioned to you, the perovskite. So if you are interested to look in detail about this graph, you can go to this website. Okay, so before we look about the material and structure, let we revise a little bit on your knowledge about how the movement of electron inside semiconductor. So as you all know, to allow the electron to flow, we can have two kinds of transport mechanism, which we call that vertical. The first one is the drift, and the second one is the diffusion. The drift current, if you read over there, is depend on the external force, which is in this case is the electrical field, E. And for the diffusion, it looks like the gas is depend on the concentration. So if you want to know how much the current flow inside your material, you need to know how the transport mechanism. Is it a drift or is it the diffusion? Or both, can be both. Drift, just I mentioned before, it will be related with the external force, which is the electrical field, and this current depend. This one is the carrier concentration. The numbers of electrons. So you need to have electron to have a current. If there is no electron, there is no free electron, there is no carriers, so you cannot have the current. So how to calculate it? You need to find what is the carrier concentration. And usually to calculate the carrier concentration, we considering what? The density of state and also the Fermi Dirac distribution function. Density of state means inside that energy level, there is allowable state that electron can be existed. Are you all still with me? Okay.
Sorry, can you repeat that?
The density of state, I just draw with, to you all before the energy band diagram. We can have the conduction band, we can have the valence band. And how to calculate the numbers of free electron? Free electrons are inside the conduction band, right? If electron inside the valence band is not moving, is bonded with the length. To calculate this, you need to know how many states available that can allow the electron to be existent over there. Because we cannot know the exact time and the exact position or the exact energy the electron is there. That is the quantum mechanics. But so how can we deal it? We use the probability. Okay? And then this density of state said to us, if this is a three-dimensional material, you will have this much of state that available. But you still do not know this electron is there or not. That's why we need to multiply with this distribution function, the probability. And we follow the Fermi-Dirac probability. You can have Boltzmann, Bose-Einstein, and so on. So we multiply with the Fermi-Dirac, either 0 or 1, either existent or not existent. And then you can calculate the numbers of carrier concentration. So when we know these numbers of electron, then when we know the speed of that electron, the flow, then it will become the current that flows inside. The unit of current, I, what is the unit? Ampere, right? Ampere. In terms of single SI, Coulomb per second. So the total charges. So this is how can we calculate the total charges that move inside the material. And then this speed is depend on the external forces, which is the electrical field. So this speed, the drift velocity, which is the average velocity of electron, is proportional to that electrical field that we apply to the material with some constant. And that constant we define as a mobility. How mobile the electron can move inside the material. And this mobility is defined as E is the electronic charge, tau is the scattering time, and this m star is the effective mass. This we call that
Effective mass
of electron. You can imagine, it's not truly correct, but for imagination. How many of you watch Dragon Ball? You know Dragon Ball? You see Goku training outside of the universe. He put weight. If you take in Earth, different in planet Mars.
gravity.
Yes, different mass. Electron in the vacuum. How much the mass? 9.1 multiply 10 power of minus 30 100. You can Google that. Kilograms. That is the mass. However, if you put inside a material, we cannot consider that mass. We consider it as the effective mass because, like Goku is in different universe, you will have different mass. Where this come from? In a material, for example, like the single crystalline material, you have all the lattice is crystalline. Look like that. Fixed. Equilibrium. And each atom, for example, if I consider only one direction, it has the potential. Look like that, because it has the class, nucleus. And this potential, if the electron are outside from there, it will interact with that potential. And how can we describe this potential inside a material? That's the mass. The mass will become difference. And we call it as the effective mass. Okay. So how mobile it is depend on the mass, and it's also depend on scattering. What is scattering? Just the name scattered. In the material, it's not only electron. We have the lattice. Lattice is the atom that we define as a wave, periodically. So it has the interaction. That kind of interaction also we can consider it as a phonon scattering. The scattering with the phonon. Phonon is the lattice. And then we also have the other kind of electron. For example, we also can have electron scattering. It can collide with each other. So that kind of scattering process. I think if you recall back when you learned about electronic physics, for example, there are two main scattering processes. One is the ionized impurity scattering. As I mentioned before, why we are using semiconductor? Because we can alter the carrier concentration. We can increase the numbers of electrons. How can you increase it? By inserting the other type of atom, or by doping. For example, like silicon. If you want to make it N-type materials, you want to increase the numbers of carriers. You will dope the silicon with phosphorus. Silicon has 4 electron valence. When it makes the bonding to form a silicon lattice, that forehand will have 4 silicon, right? If you put phosphorus, phosphorus has 5 electron valence. If you put 1 over that, it means that there is 1 extra electron. That extra electron will become 3 electrons. When it loses 1 electron, the phosphorus atom, it becomes what? Ion, right? It becomes charged. So this ion will also interact with that electron. That's why we call it as the ionized impurity scattering. The electron scattered with the ionized atom, in this case, is the phosphorus atom, to make it N-type. And the other one, the most governing scattering process, is the phonon scattering, which is the lattice itself, the silicons. Okay, so by using this kind of scattering process, effective mass and mobility and so on, we can estimate how much the current when you apply the electrical field, when you know this material properties and the numbers of electrons. Roughly from the equation, you can see that if you want to increase the drift current, you need to increase the carrier concentration, or you need to increase the electrical field, or you need to increase the mobility to find the material that has the higher mobility. That is for the drift current. How about diffusion? Diffusion depending on this carrier distribution or the electron distribution inside the material. Like the gas, it will tend to move from higher concentration region to the lower concentration region. So this kind of transport, we call it as a diffusion transport. The current is equal to that change in that distribution with sum of constant. This constant we call it as a diffusion coefficient. And it depends on the material. So the total current inside the semiconductor, if it has the electrical field and if it has the distribution of the charges, all will become summation. The ending of the transport. We have the electron, we also have the hole. We have two kinds of transport mechanism, the drift and also the diffusion. Okay, I hope you all have recalled a little bit about that semiconductor. One more thing, because we will discuss about PN junction. When we have this P-type and N-type semiconductor, and we connect it electrically, what will happen is we will have this space charge region due to the diffusion process. Inside the N-type, we have many electrons. Inside the P-type, we don't have many electrons. As I mentioned before, the electron will tend to go from higher concentration to the lower concentration. That's why it will become more positive inside the N-type and more negative inside the P-type due to this diffusion process. And this space, we call it as a space charge region. And I think if you recall back, when you learn about PN junction, you will consider this energy band diagram. So before we combine it, we have the P-type. So this is EC, this is EV, the EF is here. For the N-type, where is the EF? The Fermi energy. Near to EC or near to EV? Near to EC. Near to EV. So N-type is near to EC. Okay. EF we can consider as to show us the numbers of electrons. When it's near to EC, it means that that material have more electrons. When it's near to EV, it means that it has more hole inside the hole. So when you connect it electrically, what will happen is, due to the diffusion process, the numbers of electrons will go towards the P-type and the hole will go to the N-type and it will become equilibrium. The EF will be same. And what happened to EC and EV is mean that it need to keep this distance. It need to keep this distance. Because outside from this region is still the neutral N-type. So this EC will go down to here and this EV will go down to here, so that you can see the band is bending. Look like that. So when you have the band is bending, you know that we have the space charge due to the length of that electron and holes. The plus and minus will tell us that it has the internal electrical field to stop the diffusion process to go more than that. Okay. So when you see the energy band diagram is bending, it means that it has this internal electrical field, so that you can stop more bigger space charge region. become equilibrium. So this is the energy band diagram that you all have learned before, and you can see that it becomes like this. So this is the PN junction. We call it as the PN junction. And this PN junction can be look like, or one of the electron components is the diode. So if you supply voltage between the PN junction, you can have forward bias, you can have reverse bias. Forward bias means when you apply negative at the N type, positive at the P type. Reverse bias, you have applied positive at N type, negative at the P type. Reverse and forward bias. And if you measure the IV characteristic of the diode, by applying the voltage, you can get this kind of line. And here is not zero, because you have the reverse bias current, the leakage, quite small, very small. So you can make use the diode as a one direction current flow, and also use it as a switch on off at the threshold voltage. And I will not discuss about how to derive the diffusion current based on this PN junction. That one you can recall back by yourself what we have learned. But we will have that current in terms of exponential equation. With the Js is the saturation current, which is the reverse current. If you look carefully, this is similar like the equivalent circuit of the solar cell, the diode, but in a different opposite. Turun ke bawah. Go down like that. Right? Okay. Roughly, what happened when you give the photon energy? Photon energy, hν, depend on the frequency. You apply the photon energy to the PN junction. You can do experiment like this, and then you connect with some load, and you can try to measure the current. Measure the current. And you can see the current start to flow. I have a question for you all. Maybe some of you will think, why we want to difficult ourselves to make a PN junction? Why not we just use N-type material or metal? Metal has many electrons compared to the semiconductor. Okay, let's take metal, copper, for example, copper. And then just give the photon energy. Should have a current, right? Okay, so if I give you the task, you don't have the experimental things. You can buy copper, you give light, for example, not heat, light, not heat, light. Light, and then you measure the current. Who will say we can see the current flow? Anyone? Who will say there is no current flow? What we can expect, there is no current flow. You can try. Maybe some of you thinking, why we need to do PN junction? We have the few catalysts in the N-type. Just give the photon energy, so the electron can have the energy to flow. But it's not happening. But if you can do that, you can publish a good paper. We will discuss that after this, when we discuss about the step to make a solar cell. Okay. So in this case, we have the PN junction, and we give the photon energy at this space charge region, and we can see the current start to flow. That IR. Current start to flow, and then when we connect it with some load, with the resistance R, this load or this R, we have a voltage drop, positive, negative, like that. Resistance is the passive element or active element? Passive, very good. It's a passive element based on the rules of direction. The current flow going towards positive is a passive, right? Passive element. So if this is positive, this is negative, you can see that look like we apply a reverse bias to the PN junction. When we apply the reverse bias, it means that we will have, forward bias, negative, positive. Forward bias, this means that there is a forward bias current. So if you want to know how much the total current flow towards this load I, so the produced photon current IL minus with that forward bias. And this IL on this forward bias is the equation based on that diode equation. So the diode is look like this, right? So if IL is the maximum current, it start over here, it will be reduced by this one. So that's why the IV characteristic we just discussed at the initial slide. We have this ISC, VOC, and the maximum is this shape, this question. So that's why we can have the equivalent circuit in terms of diode over there, plus with the two kinds of resistance to consider the resistance of the contact and also the resistance to the leakage or the defect inside the material. You all prefer me to do until 6 o'clock or a little bit earlier? Prefer until 6? No. Tired, right? That's all right. I think I will start around 5:30, 5:42. Okay. To make a solar cell, we need to have these 4 basic steps. So you can read over there. First one, just I mentioned before, we need the absorption. We need to absorb the light. We need to absorb the energy. If you don't have input energy, how can you convert it? Cannot, right? So you need to absorb it. After you absorb, you need to produce free negative and free positive charge. If you don't have carrier, how can you make the current to flow? If there is no carrier, means the electron and hole are bounded with the atom. So you cannot make the current flow. First, you need to absorb, use that energy to excite the electron to make a free pair of electron and holes. Number 3, discriminating. You need to make the electron and hole to move at different way. This answering the question I just threw before this. Why not you just use a type of copper if like get the type? This is the reason. You need to discriminate. You need to make electron to move one way, the hole the other way. If you don't have that action, we call it as the photovoltaic action. If you don't have that kind of action, the electron and hole, we try to be equilibrium. We try to recombine them. And we don't have energy enough to move. Because the energy that you supply is only enough to make it excited at higher energy level, but not to make it move around. You need some more energy to make it move around. So that is number 3, the discriminating mechanism of that free electron and free holes. Number 4, you need to have the current start. So to make this happen, usually for the solar cell, we will have this kind of structure. You have 2 layers, the main layer over here and over here, and then you have electrode at the top and at the back. And that electrode, you connect it with some resistance to use that power. And then you expose it to the light. Other than that is to improvise the performance. For example, like the coating and so on, to have the anti-reflection. We want to absorb all of that energy. So you need, in the case of, I think the simple solar cell is the PN junction. So you need to have P and N type. And then you need to have electrode to allow the current to flow outside from the solar cell or to connect with that loop. So, okay, first, let's look about Venn diagram. I think we just recall back a little bit. One more. I have showed you the EC and EV, and we know that this is the band gap. Okay. And then we know that electrons are full inside the valence band and empty inside the conduction band. So if you want to make a free electron, you need to supply energy to this electron to go up at higher energy level inside the conduction band. E. So this one is depending on the energy band gap. We have the other level that we call it as the energy of vacuum level. If you put your material inside the vacuum and you give energy, much bigger energy, the electron can go up until above than the vacuum level. So it means that you can take out the electron from the vacuum. So this is the concept, for example, like the old television, for example. The tungsten, you want to take out the electron to move inside the vacuum. I think the old television, the big one, the tube. Other than that, we use the so-called secondary electron. That one we are using to characterize or to see the small world. To see a nanometer or the things, we shoot electron, and then the reflected electron will be changed into an image. That one we call it as the scanning electron microscopy. Maybe some of you in final year project and so on, or your master project, are familiar with this kind of characterization. Okay, inside the band gap, we also have this localized state. Sometimes the electron can be trapped inside the energy band gap. Why it can happen? Defects. We cannot make a perfect material. There are some defects. And if we go more smaller world, for example, like a molecule, this EC and EV. EC we call it as LUMO, and EV we call it as HOMO. LUMO means the lowest unoccupied molecule orbital. HOMO is the highest occupied molecule orbital. But the image you can consider same like EC and EV for a small scale. Okay. And one more thing, for semiconductor, we also have electron affinity. So this electron affinity is the distance between EC and that vacuum level. That is for semiconductor. For conductor or metal material, we not consider EC and EV because the EF already inside the EC. For metal, EF are here, so we only consider the energy difference between that vacuum level and Fermi level for metal material. And that one, we call it as work function. Work function. Okay, some introduction or some revise back about the energy band diagram. Why I want to recall back that? Because we need to check, we need to know what kind of absorption process that can contribute to that photo current. So it depends again with the energy that we supply. E equal to H mu. You increase the frequency, you increase the energy, the photon. And here, show you the alpha. Alpha means the absorption coefficient of the material. And you can see that we have process 1, 2, 3, 4, 5, 6. 6 kind of process can happen at specific energy. The process 1 at lower energy is a free carrier absorption. What happens is the electron is only go to the other energy state inside the band. If hole inside this is EC, this is EV. So electron are moved inside or transition between the energy state inside the band. It's not intra-band, but inside the band. That is what happened for the free carrier concentration at lower energy. The second one, a little bit higher energy. What happened is the energy is absorbed by the phonon. Phonon is the lattice. So what happened when phonon absorbs that energy? It will change the phonon mode. Phonon is vibrated like a wave. And you can have acoustic and optical mode of the phonon. So at this energy level, it only will influence that phonon absorption. When you increase a little bit more, number 3, phonon-induced transition between state in the gap. The energy is enough to make the electron to jump at this much or this speed. Not intra-band yet, but within the localized state. Number 4. Excitant producing absorption. So this one are usually in organic material. It's between molecule, become ion, for example. Because we will not discuss about organic material, we jump. Number 5, band-to-band transition. So if you increase more, we can have the energy absorbed by the electron, so the electron can go intra-band. From valence band to that conduction. This one we want for our source. And last one, this one at lower energy level, we can have electron hopping. So this electron hopping usually at the same state or at the same energy level. Electron just hopping. Okay, so you all know when we have absorbed the energy, at least we can have this 1, 2, 3, 4, 5, 6 kind of absorption processes. Okay, take example. A function of G depend on the wavelength, depend on the position. And usually we will consider process 3, 4, and 5 because it helps the electron to go from valence band to the conduction band. So this function determines the number of process 3, 4, and 5. So it means that if you increase this number, you increase the number of free gases. And how can we relate with the absorption coefficient? Is this G function is defined how much the intensity that we receive. With some coefficient that we call it as the absorption coefficient, the material properties. And this G function is depend on the thickness. Because the light intensity can be reflected, can be bounded inside it. So this is just typical example of some material, absorber material with the thickness of 210 nanometer, and we have two kind of lambda. This one is 300 nanometer, and this one is 500 nanometer. So you can see that depending on the position, the thickness, the numbers of process 3, process 4, and process 5 become different depending on the thickness. Okay, recall back, if you have a material, the PN junction, and then at one point, for example, this is inside the P-type, for example, and then you have the N-type, right? Okay. At X1, for example, if you recall back, when you learn about PN junction, the current must be same. Right? You cannot have a different current. It is in series, not in parallel. The current is same. So when the current is same, it means that the current density before X1 must be equal to the current after X1. Is it correct? Right.
Yeah.
This is the current the continuity model that valid inside the PN junction. However, in the PN junction, we give photon energy, and then there is electron excitation, electron and hole, free carriers. And then we have the photovoltaic action, electron flow one way, hole flow one way. We produce new electron, or we increase the numbers of electrons. When you increase the numbers of electron, roughly from the current density equation, we know that the current density is increased, right? So this one, if we put it over here, that Jn minus x1, we consider as 1. If we don't have that kind of phenomena happen, it equal to the position after this x2, right? Jn x2. But in this case, because we have this photovoltaic action and free electron happening, we need to plus with the current resulted from the numbers of that three processes, right? And then we need to minus. There are some probability that this electron, even though we keep producing it, there are some probability it will be recombined back with the hole. So that we need to minus with that recombination process. So these are the total current inside that PN junction when we consider the influence of the production of free carriers that moving one way, electron one way, the hole F1. Recombination process. We can have 3 kinds of recombination process. But roughly, we can divide into 2, radiative or unradiative. The first one, the radiative recombination. The electron can recombine back with the hole. When it combines back, it means that it will lose some energy. And that energy will become light, or the photon energy. It radiates back the light. So if you look carefully, like this one, what kind of application that you can do?
LED.
Correct. LED. That's why the PN junction diode can be also LED. Okay. And the other two is non-radiative. We can have the recombination based on Shockley, red hot, or the Auger recombination process. I will explain a little bit after this. And through this recombination, we also can have the electron is trapped inside the gap between the energy blended, because we have defect and we have localized state. So electron can be stuck over there. So this will also reduce the numbers of photon current. So just I mentioned, we can have radiative that produce the light, and we can have non-radiative. So this one is number 2, the Shockley. Okay, so it is based on the state inside the bandgap. Either it can be trapped, or either it can drop to that state and release some energy. The Auger is give when it drop, recombine back, the energy is transferred to the neighbor electron. It's not changed into the photon energy, but the energy is absorbed by the neighbor electron, and that neighbor electron can go to the higher energy state. So that is what phenomena can be happening inside that solar cell. Even though we are successfully making the pair of the free holes and free electron, but it can be reduced by this kind of recombination. So when we want to calculate the current, we need to consider all of these phenomena. Okay, I think I stop until absorption. Next week, we will start on the photovoltaic action. How can we separate the free electron and free holes? Until here, any question? I stop recording. Okay. No question. If there is no question, I hope you all have